AP Calculus AB, Unit 8, Day 6 lesson. All right, there's a warm-up, 3 problems on it. I want you guys to try these out, see how good you're getting at U-substitution or just integration techniques. So pause the video, try these out. Okay, assuming you've tried these out, I would maybe shoot for the denominator to be my U. Just something to try first. If derivative 1 is 0, derivative cosine is negative sine x dx. I don't want the negative, but other than that, it's perfect. X sine x dx. So put the negative in front. Get du over u. And so that's going to be negative natural log of the absolute value of u plus c. So it's going to be negative natural log of the absolute value of 1 plus cosine x plus c. Now, I don't need these absolute values because cosine, the range of cosine is from negative 1 to 1, right? It's this curve, it goes like this forever. If you add 1 to it, it shifts it up 1. It's always positive. So final answer should be negative natural log of parentheses 1 plus cosine x. If you don't put the parentheses for your final answer, you lose points. So there you go. Next one, we could try what's in the denominator, 1 minus x to the 6th. But the derivative of that is no good. Negative 6x to the 5th dx. I need x squared dx, so that's not going to work. So then I started thinking, maybe this is like inverse sine or something. Needs a 1 there, already has it. But what would you put in here to get x to the 6th? It might have to be x cubed, right? And that's perfect, because the derivative of x cubed has x squared in it, right? 3x squared dx. Don't want the 3. It's fine. So rewrite it 1/3 integral of du over the square root of 1 minus u squared. That's inverse sine of u plus c. Final answer, back in terms of the original variable, inverse sine of x cubed plus c. All right, next one. We could try the whole denominator first, or at least in our head. But it's not going to work because I get an e to the 2x dx and I need an e to the 1x dx, and that's not an easy thing to fix. Can't do it. All right, so what we're probably looking at is maybe inverse tangent. What would you put in here? Squared to get e to the 2x, it'd be e to the x. That's going to be your u, and that's perfect, right? Because du of that's going to be e to the x dx. That's what we wanted. So this is going to be du over 1 plus u squared. So that's going to be inverse tangent of u plus c. So that's going to be inverse tangent of e to the x plus c. There you go. All right. Now, we've been doing a lot of indefinite integrals. Those are, these are the ones that don't have any limits. But today we're going to talk about definite integrals. Definite integrals have these limits. So we've been doing indefinite integrals like this. We're like, oh, it's x cubed over 3 plus c. Cool. All right. That's what we've been doing. But now we're going to actually start plugging values in. So what we were getting before is sort of like formulas for the area under curve. Now we're actually going to find the area under the curve between 2 points. So let's see. What we are going to do the antiderivative, x cubed over 3. We could write plus c, but then we put these brackets around it and we put the limits on here. Okay, we usually put them on the right side. Now what we're going to do is we're going to plug the 5 in first, because the whole idea, this goes back to like the first day. This is the curve. This is a picture of that parabola. I'm trying to find the area between 2 and 5. So all that area right there. Now, what this does is this helps us find the area from some point to 2 and to some point to 5. So we want to calculate the bigger area first. I'm going to calculate all of that first, and then calculate this little chunk and subtract it to get what's in between. So we always plug the further right one in first. And then we always plug in the left one, the smaller one, next. And we subtract because we're trying to get the difference between them. So it's always subtraction. Now, what you might notice happens with the C's is that the C's drop out every single time. Every time. Even without knowing what C is, they always drop out for definite integrals. Indefinite, you need it. So we're just not even going to bother writing it in the future if you guys are cool with that. I mean, you could if you want. So area in its problem from 2 to 5 is a really nice number, 39. So why are we doing this? It's the area between 2 and 5. We get 39. Okay, why do we subtract? Because 125 over 3 is the area from 0 to 5. And 8/3 is the area from 0 to 2. So if we want it from 2 to 5, we subtract the small area from the big area. Perfect. You guys ready for it? The fundamental theorem of calculus, part 1. The fundamental theorem of calculus. I mean, this sounds really important. This is calculus class, right? And this is the fundamental theorem of calculus. Like, this sounds like the most important thing ever. And it, it kind of is. It kind of sums up everything. What it says is, and this is just, I wrote it like this is the way the book writes it. They use this little f as capital F. They say the derivative of capital F is little f. In other words, we could write this maybe in a way that's a little more clear. If you integrate f prime, capital F prime, which is what little f stands for, integrals undo derivatives. So you get the original function. Perfect. That's the basic idea that I think we've been relying on, right? Integrals undo derivatives. So if you put a derivative inside integral, they cancel each other out. If there are limits, you got to plug limits in after the fact, like you usually do. And that's it. That's the fundamental theorem of calculus. It says that integrals undo derivatives, plug in the limits. Part 1. Okay. Another way to think of this is capital F of x is the antiderivative of little f of x. I don't know if that makes any difference, but I kind of like just doing this right here, just all one letter. It's not a formula to memorize. It's a basic idea that we've already been relying on. If you integrate derivative, they undo each other, you get the original function. You plug limits in like we started talking about today, top first, bottom second, subtract. So, based off the work we've been doing up here, if you integrate f prime, you get f for the antiderivative. Don't have to write plus c. You can plug limits in still first. You do the top first and the bottom second. That's it. Now, I don't know. Can anyone in here think they can predict what the fundamental theorem of calculus part 2 is? So part 1 pretty much says integrals undo derivatives. What do you think part 2 says? Anyone say derivatives undo integrals? Because you'd be right. Just the other way around. Same idea. Integrals and derivatives, they undo each other. Either way. Okay, so now that we're doing definite integrals, let's talk about some properties of definite integrals. So properties are kind of like things that are true about them. So, and I'm going to try and, kind of back up my conclusions, even though I think some of them will probably seem pretty obvious. One will be a little hard to wrap our head around at first. So if we're integrating a function from a to a, let's see what happens. Well, this is like that whole thing. This is like f prime, right? I'm kind of using the same notation for both tests. The antiderivative of little f is big F. You're going to plug limits in. If it's a to a, you get f of a minus f of a, which is 0, right? I mean, just think about it. You're saying, let's take this curve and let's try and find the area underneath it from A to A. So it starts and ends at A. So how much area is under that? No area, right? So if you integrate from one point to the same point, of course, it's going to be 0. That totally makes sense. That's an easy one, right? 0. Okay, now this other one, okay, if we integrate from B to A, then antiderivative of little f is big F, and plug in FA first and then FB. But if we were to relate this to, so here's the deal. Usually, just alphabetically, I'm going, A, little a is to the left, B is to the right, and we're finding the area underneath here. And so if we were to do A to B, left to right, which is what we usually do, we get big Fx from A to B, and then we get FB minus F of A. Okay? But if you flip them, if you flip the limits, you're going to get the same answer, except it's going to be negative, which you kind of think of, instead of going forwards, you're going backwards. So you get the same number, the same value, the same area, but you're going to get the opposite sign because you're going backwards. Okay? So now the areas are the same algebraically. Like, it's the same area, okay, but not the same, okay, but the areas aren't going to be the same answer. Normally we go left to right. Okay, normally we go left to right. Left to right. Okay? If you go right to left, and you could do the work. I just did it. If you go right to left, you're going to get the negative of the other one. Okay? So B to A is the same as A to B, except you get the opposite sign. So that's that conclusion. Now, the next one's a little harder, I think, at first to think about. The first version of it totally makes sense. It says, okay, if you want to find the area from A to C, you could find the area from A to B first, and then B to C, and you could add them up, right? And that's the basic thing. It goes A to B, f of x dx, plus B to C, f of x dx. You can break integrals up, like the limits, okay? Now, we're going to run some weirder applications of this idea. So let's just put some areas on here just for fun. So the area from A to B is 5, B to C is 2. Okay? 5 plus 2 equals 7 for the whole area. Now, check this out. You might notice this. Check this out. If the top limit matches the bottom one, it's like you can connect them together and get A to C. It's kind of like in geometry, you use this idea called the transitive property for like, I'm trying to remember what the application was. Yeah, it's the transitive property. Transitive property, this is what it was. Transitive property, and it could be for, I think, let's see, transitive property. It says it of equality. If A equals B and B equals C, then A equals C, right? That's the transit property. Now, this is not the transit property, but it makes me think of that if you have some common thing in the middle connecting it, you can just connect them together and cut out the middle part. And, that's kind of how it works. But here's the crazy thing. We can actually do it. We can mix it up in any order. So what if I said A to C plus C to B? I'm telling you, it's just going to be the same as A to B. Now let's check it out. Now this picture isn't accurate, but I want to use the same values. A to C is 7, right? That's what we just got done. A to C is 7. C to B is -2 because it's backwards. And so if we do 7 plus -2 equals 5, is that the same as what A to B originally equaled? Yep, sure enough. What if we did B to A and then we did A to C? Well, the top here matches the bottom here, so it should give you the same thing as B to C. Top matches bottom. Okay, well, B to A originally would be -5, right? Because A to B was 5, so B to A would be -5. A to C was 7. That was the whole thing. So it's going to be -5 plus 7 equals 2. Is B to C equal 2 in the original problem? Yep, it did. So it's kind of a weird thing that you can use that kind of like connecting, breaking it up, but you can kind of like totally mess with the order. It doesn't have to be so strictly just left to right, nice little chunks. Okay? On the homework, you're going to be asked to do some problems algebraically and some of them geometrically. Now, geometrically means use geometry, use a picture. Okay, so like in this problem right here, you say, well, I could graph that line, y equals x, and I want the area underneath it from 0 to 6. I want that area. You say, oh, well, that's a triangle. 1/2 base, which is going to be 6, times the height, which is also going to be 6. And so it's going to be half of 36 is 18. So that's geometrically. How about algebraically? Algebraically is doing it with actually integrating it. So bump it up 1, divide by 2. Don't need the plus c on these. Plug the top limit in first, then the bottom limit. And so then you're going to get 36 over 2 is 18, minus 0 is 18. Same answer. So that's algebraically, that's geometrically. They should get the same answers. Now, this next one, let's see. What do you guys think? Even before we graph it, it's going to be, if we look at this is going to be -6 to 6. Right? So is that just going to be 18 and 18? Because the area of this is 18, and the area of this is 18. So is that just going to be 36? Wow. 36. Anyone else have a different idea? Maybe what it might be? Maybe someone says 0. Let's try it out. Let's try it out algebraically. Bump it up 1, divide by the new exponent, -6 to 6. Plug 6 in first, minus, plug -6 in second. 36 over 2 is 18, minus -6 squared is positive 36, divided by 2 is 18. The answer is 0. The reason the answer is 0 is that this value comes out to -18. And that's because it's below the x-axis. So anytime the area is underneath the x-axis, you're going to have a negative. Now, area itself can't be negative. There's no such thing as negative area. So what we do is we call it signed area. So it's either positive or it's negative area. So it's not really area, but it's associated with the area. Okay? So here, for instance, that's going to be negative 18 because it's from negative 6 to 0. Now, if we went right to left, you'd get positive 18. Now, if we do the work, x squared over 2, this should give us the right answer still. 0 squared minus negative 6 squared gives you 0 plus 0 minus 36 over 2 gives you negative 18. So, gives you the right answer that way. All right, last problem. And I guarantee you I'm going to give you a problem like this in your next test, and people are going to really struggle on it, which I think it's kind of a nice, easy problem. Now, we could draw a picture. This is a piecewise graph. Okay. It's a piecewise function. So, I guess we could graph this up to over 1, right? Up to over 1. So that's that line. And then 2 is just a flat line. And when x is greater than 1, it's the flat line. So open dot, arrow to the right. And then solid dot on the y equals 2x line, which is right here. So this is a nice continuous graph. It's not differentiable, that's for sure. Okay, so that's the graph. We're trying to find the area underneath it from negative 2 to positive 4. So I guess like this area right here. So we could do that, I would recommend doing that geometrically. Now, by the way, when we rewrite this, so it's split it up, I would do this chunk and this chunk separately. For this chunk, I'm going to put the 2 out front. Now, when you split it up, they each need to get dx's. So I'm splitting it up first, okay? And right now I'm working on this. This area right here is just going to be that right there. So the area is going to be the area of this triangle. Base is 2. Height is, if you plug negative 2 into this equation, you get negative 4 for the coordinate, negative 2, negative 4. So the height's negative 4. So it's going to be 1/2 base times height. 1/2 base times height. It's going to come out negative because the y value is negative. So it's going to be negative 4. So negative 4. And there's a little triangle here or a trapezoid. It's either a triangle and a rectangle or a trapezoid. This is going to be 1/2 base times height. So that's going to be 1. And then this is that's a rectangle, right? Base is 3, height is 2, you get 6. Right, that's that. Plus this, we could integrate. We could integrate, or you could imagine what this graph looks like. This is a flat line going through 3, right? And I want to find the area from negative 2 to 4. Like, that's just a rectangle. Anytime you integrate a constant, the graph is like a rectangle. So this is base times height. The base is distance from negative 2 to 4, which is 6. The height is that number inside, which is 3. So 2 times 3 is 6. 6 times 3 is 18. The answer is 24. So that's how I would do that problem. Okay, today's assignment, 2 different pages out of the book, a bunch of problems from 393, evens. I should probably put those online. There's so many evens. And then also page 414, do 11 to 20 all. Check your odds in the back. I'll try and put the evens online. So let's see. Let's try and practice these.